Hello, my Peninsula Geometry scholars. We're moving on to 5.2 today. We're going to talk about congruent polygons. So it's sort of a larger category, whereas this whole chapter is about triangles. And this idea will cover all polygons that are congruent. So we're going to talk about some things called corresponding parts and congruent figures. So we're going to identify them, and then there's a third angles theorem that we're going to use specifically for triangles. So let's go through a couple of examples. First of all, basically, if you have two figures and they look exactly the same, if they are congruent, then the parts that are in the same place are exactly corresponding. So if and only if you can do a rigid motion or a composition of rigid motions so that one figure is mapped onto the other, that's what we would call congruent. So that was from chapter 4. Now, if they are congruent, then each part, whether it's a side or an angle or a point or a vertex or whatever, that is in the same location on the other one is equal or congruent. So we can write what's called congruence statements. We can say that this angle is congruent to this angle, or this side is congruent to this side, or this triangle is congruent to this triangle. And that's, you see the picture here, where we've got these corresponding angles. A corresponds to D, C corresponds to F, B corresponds to E, because you'll notice their tick marks are the same. Now, if it's hard for you to see, I would always recommend like rotating the figure. I would actually redraw it on my paper. Some of you may be able to do it visually, or you could just go by the fact that they have the same tick marks. So ED and AB both have 2 tick marks, so they are congruent. EF and BC are congruent. But in this case, if you're talking about whether you write CA or is congruent to DF or CA is congruent to FD. In this case, order does matter. So if you start with, say, angle A and you go to C and you say side AC, then you have to go from where A corresponds to, which is D, and then you would say side DF. So it's side AC is congruent to side DF. So see how that has to be in order, which pay attention to the colors because that does matter. Small study tip here. If two triangles are congruent, then all their corresponding parts are congruent. So there's 6 parts to a triangle, 3 sides and 3 angles. All 6 parts are congruent. And then if the corresponding parts of 2 triangles are congruent, then the triangles are congruent. So if the parts are congruent, then the triangle is both ways. Further, if you can reflect so that you take ABC and you can change it with some kind of rigid motion or an isometry that we mentioned, if you reflect it and then rotate it, well, then you can, that's sufficient to know that they are congruent. So here's an example of the first type of problem where you're just identifying the parts. Again, watch how it's rotated.
Write a congruent statement for the triangles. Identify all pairs of congruent corresponding parts. Solution. When you write a congruent statement, always list the corresponding vertices in the same order. To help you identify corresponding parts, rotate triangle TSR as shown. Now, from the diagram, you can see that vertex J corresponds to vertex T, vertex K corresponds to vertex S, and vertex L corresponds to vertex R. So the diagram indicates that triangle JKL is congruent to triangle TSR. Next, identify the pairs of congruent corresponding angles. Angle J is congruent to angle T, angle K is congruent to angle S, and angle L is congruent to angle R. Now identify the pairs of congruent corresponding sides. Segment JK is congruent to segment TS, segment KL is congruent to segment SR, and segment LJ is congruent to segment RT.
So you can see either looking by rotating and doing the same location, or according to the tick marks. Both ways you can do that. Now, the properties of congruent figures means that if it's in the same place and it's the same size, then we can use it to solve problems. So here's an example of that.
In the diagram, DEFG is congruent to SPQR. Part A, find the value of x. Part B, find the value of y. Solution. Part A. From the congruence statement, you know that segment FG is congruent to segment QR. So FG equals QR. Substitute 12 for FG and 2x minus 4 for QR. Now solve for x. First add 4 to each side of the equation. This gives you 16 equals 2x. Then divide each side of the equation by 2. This gives you 8 equals x. So the value of x is 8. Part B.
Now
From
find
the
y.
congruence statement, you know that angle F is congruent to angle Q. So the measure of angle F equals the measure of angle Q. Substitute 68 degrees for the measure of angle F and the quantity 6y plus x degrees for the measure of angle Q. Now you know that x equals 8, so substitute 8 for x. Then solve for y. First subtract 8 from each side of the equation to get the equation 60 equals 6y. Then divide each side of the equation by 6. This gives you 10 equals y. So the value of y is 10.
Hopefully you can see how that's a problem you can solve. Again, a review of your algebra. The concepts, right, for this new section is those things are equal, so you can solve for them. So now we're going to move on. This example is showing that two figures are congruent. It's like a little paragraph proof, and it's not nearly as useful. I'm going to skip this one to keep the video shorter because I'd like to go on to the theorem. So we have a theorem that basically says that if you have specifically congruent triangles, then triangle congruence between two triangles is reflexive, symmetric, and transitive. We've been using those properties before, and each one of these, you should be able to see that it's triangle ABC is congruent to triangle ABC. If ABC is congruent to DEF, then DEF is congruent to ABC, symmetric. And transitive, if ABC is equal to DEF and DEF is congruent to JKL, then ABC is congruent to JKL. That's going to come in really handy in the future. And just for an extra tip, the properties of a congruence that are true for segments and angles are also true for triangles. So that's why they also have reflexive property of, symmetric properties of. Well, it just transfers right on through to triangles. So we have one theorem in this section. It's called the third angles theorem. It'll be really handy. But as you can see, if you have two triangles, we've got ABC and DEF. If you know that two of those angles are congruent, so B is congruent to E and A is congruent to D, then you automatically know that C has to be congruent to F, because all triangles have to add up to 180. So they're going to be exactly equal. There is a proof in your book. We may go over it under the camera, but not right now. It's almost self-explanatory. So what we'll do is just use the theorem to solve problems. So here is an example, and watch the two separate triangles closely.
Find the measure of angle BDC. Solution. From the diagram, angle A is congruent to angle B, and angle ADC is congruent to angle BCD. So by the third angles theorem, angle ACD is congruent to angle BDC. By the triangle sum theorem, the measure of angle ACD equals 180 degrees minus 45 degrees minus 30 degrees, which equals 105 degrees. So the measure of angle BDC equals the measure of angle ACD, which equals 105 degrees by the definition of congruent angles.
And if you need to see that again, pause, go back, watch it again. The other thing you could do if you didn't follow that is just redraw the two of them so that you have ACD here and then maybe redraw BCD down here and you should be able to see it then. But anytime you have two overlapping ones, the figures are going to get a little more challenging in chapter 5, which I believe, yeah. Now this kind of proof, we have a few proofs in this section, and we're going to use those properties, reflexive, symmetric, and transitive. And so I'm going to give you this example, plus I'll do another one live with you in class.
Use the information in the figure to prove that triangle ACD is congruent to triangle CAB. Solution. From the diagram, you are given that segment AD is congruent to segment CB, segment DC is congruent to segment BA, angle ACD is congruent to angle CAB, and angle CAD is congruent to angle ACB. You need to prove that triangle ACD is congruent to triangle CAB. Plan for proof. A. First, show that all pairs of corresponding sides are congruent. Notice that you are given that two pairs of corresponding sides are congruent. Use the reflexive property of congruence to show that segment AC is congruent to segment CA. B. Then show that all pairs of corresponding angles are congruent. Notice that you are given that two pairs of corresponding angles are congruent. Use the third angles theorem to show that angle B is congruent to angle D. Plan in action. Write a two-column proof. You are given that segment AD is congruent to segment CB and segment DC is congruent to segment BA. By the reflexive property of congruence, segment AC is congruent to segment CA. So all pairs of corresponding sides are congruent. Next, you are given that angle ACD is congruent to angle CAB and angle CAD is congruent to angle ACB. By the third angles theorem, angle B is congruent to angle D. So all pairs of corresponding angles are congruent. Because all corresponding parts are congruent, triangle ACD is congruent to triangle CAB.
Now, the only other thing I would have said is if you wanted to, they did step 1 and then 2 right after it, and then 3 given and 4 right after it. Technically, if you wanted to, you could also have the given statement here on the first line, or 1 and then 2, and then 3 and then 4. But it's a perfectly valid proof either way, and I hope you followed all that with the markings on the section. I think that's it. Yeah. So we're ready to do our BIM. I am going to show you 1 or 2 more examples in class, and the notes are in the notebook, but the class notebook. For now, I'm going to end this. Okay.